Welcome and hello. This is a video exercise in the FHWA hydraulic toolbox. I've titled this exercise Flow Rate and Riprap Size. And what we're going to be doing is using the channel lining design calculator as well as a channel calculator to investigate the relationship between the flow rate in a channel as well as the different riprap classes that allow that channel to be stable. Let's go ahead and get started. I'm going to start with a calculator, new channel analysis, and then I'm also going to add a new channel lining design analysis. So the channel parameters that we specify here is going to be used in our lining design. All right, so let's go ahead and get started with the problem statement. So this is what I'm asking to find. This is the introduction to the problem. Find the smallest allowable riprap to maintain channel stability for the flow range between 100 CFS and 2000 CFS. All right, and then I'm given some information about the channel. It's a trapezoidal channel with a base width of 10 feet, a 2-to-1 side slope, a 2% longitudinal slope, and then a radius of curvature of 100 feet. So we have a little diagram over here. And then we also have our crushed riprap data, which has the 5 different classes. And associated with those 5 classes is a D50 size for the material, and that's in units of millimeters. Okay. So let's get started with the channel first, and then we'll then deal with the lining and stability. I'm going to come to my channel analysis here. I'm going to first of all rename this to just call it something like channel 1. And then just to be consistent, I'll also rename the channel lining design calculator to channel lining 1. Okay. If I had a more descriptive name, I could add that, but channel 1, channel lining 1 is good for now. And also just best practice, I'm going to go ahead and save this to my computer. How about I'll just call this project 2. Okay. So we're ready to rock and roll. I'm going to right click on channel 1 and channel data. The shape or the cross section is going to be trapezoidal. That's correct. The side slope will be 2-to-1. So we'll type that in. And then the channel width, that is 10 feet, except I'm noticing my units here are in meters. So I'm going to click OK, change the units to US customary, and then click Save, and then just double click on channel 1 to open up the calculator once again. And then, okay, cool. So our units are now in US customary units. Change that bottom width now to 10. The longitudinal slope is 2%, so 0.02. Manning's roughness, this was not provided, but it's going to automatically change with the change of flow rates and the different riprap size anyway. So I'm just going to throw in a number 0.05. All right. Down below, we need to specify the flow rate. And what we're going to be doing is looking at the range from 100 CFS up to 2000 CFS. And I'm going to start at the low end of that range, which is 100 CFS. And as the exercise progresses, we'll work our way up to 2000 CFS. All right, so I'm going to click on Calculate. Here are the results, which is going to be used when we access the channel lining calculator. All right, so let's just click OK. Head over to the channel lining calculator tool. So right click, channel lining design data. At the very top, we have to make our choice for the different lining type. Now, what is already selected is what we want here: rock, riprap, and gravel or cobble. So we have different riprap sizes. The other options are shown here: vegetation, erosion controlled, or gabion. For selecting a channel, I'm just going to use the channel 1. And because we've already defined that channel data, we have those channel numbers popping in place right here. The one thing we're going to want to change about that channel is the flow rate. So if I click on the channel calculator tool, I can modify the flow rate here, click on calculate, and then the results from the channel lining calculator will be updated. Now, unfortunately, it does seem to delete the Manning's roughness value. I'm just going to go ahead and add that in, click calculate, and then click OK. All right, down below here, we need to input the D50 value. This is the median grain size of the riprap class. So let's bring that data up here. We're going to start with class 1, which has a D50 of 230 millimeters. And if 100 CFS is not stable, based on that curvature of 100 feet, then we'll just increase to the next riprap class and so on until we're stable. So let's go with 230, 230. And then we know that it's crushed. So I need to change the shape from angular to crushed. that was provided. The safety factor is going to calculate itself. And then the last thing we need to do here is scroll down and click on the curvature radius 100 feet. So when I tab off, we should have all the calculations, and we're looking good now because we're seeing green. The channel bottom is stable, the channel side is stable, and also because we have a curvature input here, 100 feet, then we also have the bend stability for bottom of the bend and the side of the bend. All right, so what I'm going to do next is increase the flow rate from 100 CFS up to basically as high as I can so that all of these stability checks are still good and we still have a stable channel. Once we cross over to high enough flow rate, then we're going to need to upsize the Riprap class to a larger D50 here in the calculator from 230 up to the next size. And then that will be stable up into a higher flow rate, in which case we're going to identify the different Riprap classes and which range of flow rates they are safe to keep our channel stable at. All right, so anyway, we have 100 CFS, that's our base flow. Let's go ahead and increase that. So I'm going to click on channel calculator. And then for a flow rate of, I'm just kind of making up a number here. I'm going to say 300 CFS. I'll click OK. And then the channel lining calculator already recalculated based on that new design flow of 300 CFS. All I need to do is scroll down and observe whether or not stability checks have passed, and they didn't. It looks like the bottom of the bend is not stable and the side of the bend is not stable. So keeping with a 100-foot curvature radius, what we need to do is decrease the flow rate to figure out how high it can be while keeping these all four tests stable, basically. All right, so back to the channel calculator. I'm going to click on, how about 200 CFS? Calculate. Okay. Scroll down. Still not stable. So I'm going to continue that process until I have a stable channel. Instead of 200, let's go with 150. Calculate. Okay. Scroll down. All green here. So now we know that that maximum flow rate for the class 1 riprap is between 150 CFS and 200 CFS. So let's just split the difference again. I'll say 175. Calculate. Okay. Scroll down. 175 is not going to allow us to have a stable side bend, but the bottom bend is stable. So again, we need to decrease. The answer is between 150 and 175. Let's just go with 160. Calculate. Okay. And then scroll down. We're good there. So between 160 and 175, I'll increase it to, how about 165? Calculate. Okay. Scroll down. Not stable. Channel calculator. 162. Calculate. Okay. Not stable. All right. So it's either 160 or 161 for the maximum. Let's go with 161. Calculate. Okay. And we are unstable. So what that tells me is 160 CFS is the highest flow rate that the Riprap, crushed Riprap class 1 can provide stability for on all of these checks. All right, so I'm going to level up back to 161, which was the first flow rate in, integer CFS. I'm not going to go to a fraction of a CFS. So that's going to be unstable. And then what I'm going to do is increase the D50 Riprap size to the next size, let it calculate, and then notice that we will have stability. So back to the next size, that is 360 millimeters associated with the crushed riprap in class 2. So 360 is what I'll type in right here for the D50 size. I'm going to tab off and then scroll down, and we're all green again because the higher D50, the larger riprap, will provide more stability and be able to accommodate larger flow rates. So now we're going to repeat that process we did with riprap size class 1. And instead of 161, let's go ahead and increase that flow rate and search for the highest flow rate that the riprap class 2 can provide stability for. Again, I'm just kind of guessing here, 1000 CFS. Okay, scroll down. We are unstable. So we know the answer is between 161 and 1000. Let's go with 700 CFS. Calculate. Okay, unstable. So we need to decrease the flow rate again. How about 400 CFS? Calculate. Okay, that is stable. So it's between 400 and 700. Still a lot of numbers to check. So how about 550? Calculate. Okay, that's stable. So it's higher than 550. I'll go with 600, just a nice round number. I'm not going to be splitting the difference every time. 600 is too high, so that was a good guess. 575, calculate. Okay. You kind of have to remember what the highest and lowest numbers you've checked are already. Okay, so 575 is good. We can increase between 575 and 600. So let's go with, how about a 583? Or I'm sorry, how about 585? That's a little bit more in the middle. Calculate. Okay. And we are not stable, so it's going to be maybe around 580 or so. Let's go with 580. Calculate. Okay. 580 is stable. Let's increase that now to 585. Calculate. Okay. Not stable at 585. 583. Calculate. Okay. 583. Okay, so it's either 583 or 584. Let's check 584. Calculate, and okay. All right, so it's 583. What I'm going to be doing to keep track of my results is just make a quick table in Excel, type in 583 for the maximum size for that class 2 riprap. We know class 3 riprap would be between 584 and some larger flow rate. So let's change that D50 size up to 510 and then search for the next max flow rate for that new range, the new riprap class 3. All right, so I'm going to go back to the calculator. D50 is now going to be 510 millimeters. And then back to the grind. Let's increase that flow rate from 584 to, how about 1200? Calculate. Okay. All right, so that's not stable. How about something a little bit less? How about just a nice round number of 1000? Calculate. Okay. So 1000 is stable. We know the flow rate is going to be between 1000 and 1200. Let's test out 1100. There we go. Calculate. Okay. 1100 is good. So it's going to be between 1100 and 1200. All right. So you get the idea here. I'm not going to do this for the next hour, but off camera, I went ahead and finished all of these calculations and I'll show you what the results were. So just go ahead and paste in what those results were. 1127 was the number we're looking for. So 1128 to 1950 and 1960 to, I'm just putting a dash here on the very ends for minimum of class 1 and maximum of class 5 because it's going to be less than 100 CFS and more than 2000 CFS, which exceeds the range of our interest for this particular problem statement. All right, so if I was going to summarize in a table of data, here is the results. This is what we just saw in the Excel. And then also I've created a plot here on the final slide. Over to the right here, we have the range of flow rates on the horizontal axis and then the riprap class on the vertical axis. So for this particular trapezoidal cross-section with this particular curvature and longitudinal slope and side slope, if you know what the flow rate is going to be, then you go ahead and just trace up. So if you know the flow rate's 1000 CFS, go to 1000 CFS, trace up to the red line, and then trace over. That tells you riprap class 3 is the smallest riprap class size that will accommodate that flow rate and keep your channel stable. All right, well, I hope that was helpful. This was a exercise video demonstrating the relationship between flow rate and riprap class for a trapezoidal channel to identify the smallest allowable riprap that will maintain channel stability for those range of flow rates.